Is my screen visible to all of you? Write in the chat box. Can you see the question? Okay, got it, got it. Okay. Let me save the chat. I am disabling the chat box for now. Later you just put your roll numbers over there. Now to start with, this is my question. Let us try to read the question first of all carefully, and let me talk about the solution part of this question, which will bring you to the domain of a new subtopic of probability theory. In the last class, we discussed about axiomatic approach to probability and how we can solve problems with the help of those axioms. Okay, and I left you a theorem for you to solve. I left with you a theorem for you to solve by yourself. I don't know whether you have tried it or not. Today's topic is, well, I'll mention the topic later on. So let us read the question first of all. A consumer research organization has studied the services under warranty provided by the 15 new car dealers in a certain city, and its findings are summarized in the following table. Now we have this information in front of us, and you can see, whenever we put something in the tabular form, it is easily understood from the from its description that this particular table gives us car dealers, those car dealers who are in business for 10 years or more, and some of the car dealers are in business for less than 10 years. And among these car dealers, some are providing good service under warranty and some are providing poor service under warranty. So this is the reflection of the physical system that is in front of you. And if you try to add the row terms, you will get here 20, and here you are going to get 30. Okay, and so that the total is 50. So that the total is 50. And if I add the column terms, you are going to get 26, and here you are going to get 24. Here also the total is 50. So in both direction, if I move on, the total is 50. Okay, so it justifies the fact that we are actually dealing with the exhaustive number of cases marked over here, which is 50. Now, what is the question? That is very important. The question, as you can see, they have this question has two parts. Let us deal with part one first of all. This is my part one. I'm numbering it, and this is my part two. The part one is saying that if a person randomly selects one of these new car dealers, what is the probability that he gets one who provides good service under warranty? Now, when the person is going to select a car dealer, in the first case of this particular problem, he is actually not interested in whether the car dealer is in business for 10 years or more or in less than 10 years or more. He is just selecting the car dealer from the available car dealers. So if I consider capital S to be the sample space containing all the car dealers, then cardinality of this set is equal to 50. Okay, and he is selecting from any of these particular car dealers arbitrarily. If he does so, what is the probability that he gets a good service under warranty? Now you look at this table once again. It's very important. The column, first column, that is good service under warranty, actually is represented over here. It contains not only the car dealers who are in business for 10 years or more, but it also contains car dealers who are in business for less than 10 years or more, less than 10 years. So actually, if you carefully observe, this particular section is your favorable number of case, because we are interested in only the good service under warranty, and he is selecting the car dealers from total sample space, that is capital S. Now, if I write that capital G is the event that good service is under warranty, good service under warranty is provided, then the cardinality of this event according to the chart is 26, as you can see. And if I am now interested in finding the probability of getting good service under warranty, then this will be 26 by 50 by classical definition of probability. Okay, so this is my probability for the first case. My second case is very important and also very interesting. In the second case, the person is randomly selecting one of the dealers who has been in business for 10 years or more. Now, what is he doing is he is actually squeezing the size of the sample space now. Okay, so if this is your sample space, capital S, which contains some car dealers who are in business for 10 years or more, and I can divide the sample space in two halves. Here, the car dealers are present for 10 years or more. Here, the car dealers are present for less than 10 years or more, less than 10 years. Then what he is now interested in, he is interested in this section only. So he is squeezing his sample space. Okay, so he is segregating all the car. He has somehow got all the car dealers and he has segregated them with respect to who are in good business for 10 years or more, or who are in business for less than 10 years. And then while selecting the car dealer, he is actually interested in this short, small sample space. Okay, so that's why I have marked it green. Okay, so in this sample space, the total number of car dealer is actually 20. So this was my problem number 1. My problem number 2 actually defines a new sample space which is smaller than size, then the capital S. Okay, so I am going to consider this sample space to be T, which defines the number of car dealers who are in business for 10 years or more. So he is selecting from this particular set, and here also he is actually craving for getting good service under warranty. So if I look at the table once again, I'll see that this is the number he is interested in. Okay, so if capital G remains your event which actually gives you good service under warranty, because you know in this type of axiomatic approach, the naming of the events are very important. So if G remains your event that you are interested in, so probability of G that you want to find will be calculated in the following manner. You can easily calculate quickly, you can calculate the probability. That will be this encircled number, that is 16, and total number of the sample space. Now the sample space is not your capital S, it has become the green portion total. So it is 16 by 20. So quickly we have got the probability, we have calculated the probability, we haven't faced any difficulty in understanding the problem. But now let us dissect the problem and let us try to understand what is happening inside it. Okay, I am now talking about the part 2, because part 2 is the topic which I'm interested in today's class. Now, if you carefully observe, when I want to calculate probability of G, okay, which is 16 by 20, now if you look at this table once again, you will find that 16 is the number which gives you those car dealers who are in business for 10 years or more, and providing good service under warranty. So actually, you are counting the cardinality of this event, cardinality of T intersection G. Look at the event T that I have defined over here. Look at the event G that I have defined over here. And that is that number 16 is your cardinality of this particular event. Both of them are happening simultaneously. Person is choosing the car dealer from the section of 10 year or more, and he is interested in good service under warranty. So we are interested in this cardinality whose value is 16 from the chart. And if I look at the number 20, what we'll find that 20 is giving you the cardinality of the set or event capital T, those car dealers who are in business for 10 years or more. Okay, so that cardinality is given by 20. Here we can do a little bit of maths quickly, and you will find that what is happening over here. Now, if I write this quantity n of t intersection G, and if I divide this quantity by the sample space size ns, and if I do the same thing in the denominator, if I divide nt by ns, nothing will change because ns and ns will cancel each other. Okay, I can do it pretty well. But once we do it, what is happening is the following. Your probability capital G, probability of getting good service under warranty, is now becoming probability of G T intersection G for the numerator part, because it is cardinality of T intersection G by cardinality of the total sample space, and denominator part is becoming probability of T. So probability of G here actually is becoming probability of T intersection G. Now here we shall not consider this notation that I have written. I shall not consider this notation because this notation is actually, I mean, quite confusing, because this notation doesn't reflect that your sample size has squeezed. So instead of writing this notation for probability of G, what we can do actually is that, to make you understand that my sample size has squeezed from S to T, I can reflect it in this notation. And what I do to make you understand that what I have done, I can write that yes, we are interested in finding the probability of car dealers giving good service under warranty, provided we have selected car dealers who are in business for 10 years or more. So not this notation, but that notation is actually will serve the purpose and will, if I use this notation, this particular thing will clearly reflect what I mean by this particular probability, which has been calculated to be 16 by 20. I am interested in this part of this particular probability that I have written over here. So let us mark it. Okay, so my today's topic is based upon this. Now I am stopping the share of this particular screen. I hope that you have taken the screenshot. I am now going to share a whiteboard, and I'm going to give you the detailed analysis of what has been done over here. So I hope that you can see my whiteboard. So what have we done is the following. We have two events. We have two events, capital A and capital B. Is my screen visible to all of you? You can write in the chat box, because sometimes I actually check, because I'm taking today's class from home. I want to check my internet connectivity. So chat box is enabled. Please tell me that you can. Okay, fine. Thank you so much. I'm disabling the chat box. Okay, let it be so that you can communicate with me. So we have two events, capital A and capital B. Just try to recall that what we did in the previous slide, we wrote this quantity. Probability of getting good service under warranty, given that you have chosen the car dealer from business, those are doing business for 10 years or more, and I used this sort of notation. Now, if I want to give a general perspective of this quantity, then I have taken two events, capital A and capital B. These two events are any events. They are not mutually exclusive. They are not, no speciality about these events. They are any events, we like to draw as capital A and capital B. It is not like that B is a sub event of capital A, not like that. They are any events. Then probability of, just look at the formula, probability of A bar B will be given as probability of A intersection B by probability of B. Okay, how to read this particular formula? We shall read it in the following manner. Probability of happening of event A, given that B has happened, is equal to probability of simultaneous occurrence of A and B divided by probability of B. So this is how we read actually this quantity. This quantity is a very useful formula, and let us mark it properly. And we call this quantity as conditional probability. So in conditional probability, what is happening in conditional probability? We are squeezing the sample size. The sample size is becoming smaller. The sample space is becoming smaller in size. So it is called the conditional probability. Okay. Now from the you can use the symmetric property of A intersection B. Let me show you another thing. Suppose someone is interested in the opposite, the mirror reflection of probability of A given B. The mirror reflection of probability of A given B will be probability of B given A. If someone wants to find out this probability, he can do the same thing. He will write probability of B intersection A by probability of A, as if all the A's have been replaced by B's and all the B's have been replaced by A's. Okay, and this is same as probability of A intersection B. It is because A intersection B and B intersection A, they are symmetric. A and B are symmetric with respect to the property, with respect to the tool intersection. So we have actually got two formulae. Let us mark it over here also. This is also a kind of conditional probability. Okay, and if you carefully observe now, you will find that probability of, if I call it equation number A, and if I call it equation number B, okay, then probability of, from equation A and B, from capital A and capital B, probability of A intersection B can be written in two ways. We can write it as probability A given B into probability of B, or we can write it as probability of A intersection B. We can write it as probability of B given A into probability of A. Just look at the formula. I'm just cross multiplying the things. Now, if I equate the two things, that will imply probability of A given B into probability of B is equal to probability of A, B given A into probability of A. And just look at carefully that what I'm doing. I can write it as probability of A given B, and I can divide both the sides by probability of B so that I get this particular formula. Why have I done this? Because if probability of A given B is the mirror reflection of probability of B given A, I am trying to find out probability of A given B with the help of the knowledge of probability of B given A, and this is nothing but yours. This is nothing but your famous Bayes theorem. This is nothing but your famous Bayes theorem. Okay. So this is your famous Bayes theorem. Or Bayes theorem is also called theorem of inverse probability. If you have come across the Bayes theorem, probably you have seen that in the Bayes theorem, in the denominator, a summation type of thing occurs. But that occurs if we suppose this event capital A we are interested in, and there are two more events, B1 and B2. Then with respect to B1 and B2, if I want to find the probability of A, then this summation type of thing will occur. Otherwise, this is the simple version of Bayes theorem or theorem of inverse probability. It's a very simple thing, nothing new in this. You can see in the syllabus that in your module 1, separately Bayes theorem has not been mentioned. They have only mentioned conditional probability. Is because Bayes theorem is nothing but a type of conditional probability. And the only difference is that if one sort of conditional probability is given, the another conditional probability can be found with the help of that. Okay, now let us come to the interesting part. Now, you think that suppose whenever we discussed about conditional probability, we considered that capital A and capital B be any two events. Now let us modify our condition. Let us modify our condition. Instead of taking any two event, let us choose capital A and capital B, which are independent. Which are independent. That means the happening of event A do not affect or do not influence the happening of the another event. Two persons sitting somewhere at some places, tossing coins simultaneously at two different points of time, or simultaneously, but they are spatially separated. If they do not communicate between them, if they don't communicate, then in that particular case, what one person gets on his end will not influence what the other person gets on his end. But if they communicate and if they say that, okay, I have got this, try to do it carefully, then it doesn't remain independent. So here I am actually interested in an event which is totally independent. So if I choose an event which is independent, then it is quite obvious that conditional probability A given that B has happened will not be given by the formula that I have shown you earlier. It will simply be probability of A. Okay, and probability of B given A, will simply be probability of B, because capital here B is not affecting the happening of A, and here A is not affecting the happening of B. So what do we get after this? What do we get? We had the formula probability of A intersection B. Let us write the formula that we have obtained from the viewpoint of conditional probability. One formula was this. Another formula was this, probability of B given A into probability of B. Now for independent events, probability of A given B becomes probability of A into probability of B, and here we again get the same thing, probability of B into probability of A. And probabilities are numbers, and multiplication of numbers are, probabilities are real numbers, positive real, non-negative real numbers lying between 0 and 1, and multiplication of number is commutative. So probability of A into probability of B and probability of B into probability of A, they are same. So we have got a new formula for probability of A intersection B when A and B are independent. This particular formula is called multiplication theorem of probability. Multiplication theorem of probability. So what does it say? It says that if we are dealing with two independent events, the probability of simultaneous happening of two events will be the product of their individual probabilities. Now, when we discussed our axioms in our last class, when we wrote that probability of A greater than or equal to 0, or when we wrote probability of A plus probability of A bar is equal to 1, I'm not writing the other statements. Consider previous class statements. Any statement you choose. These are also conditional probability. Conditional probability is a general overview. Why these are conditional probability? We cannot see the conditions imposed on that. We cannot see the kind of thing that this given that. Yeah, it is present. Where it is present, you can write probability of A greater than or equal to 0 as probability of A given that you have considered the sample space S that is greater than or equal to 0. Okay, and here you can write probability of A given that the sample space S is there plus probability of A bar given that the sample space S is there gives you the total probability 1. Okay, now if you are not feeling comfortable with this, let me say how it happens. If I write probability of A given S by the formula of conditional probability, it becomes probability of A intersection S by probability of S. Now that was your S and this was your A. S was the bigger set, A is the smaller set. So obviously probability of A intersection, obviously A intersection S will be A. And you know that probability of S is equal to 1. So probability of A by A given S and probability of A, they are actually basically the same thing, because this is becoming 1 by the axiom 2. So actually whenever we write something, actually the condition is imposed. Sometimes we overlook the conditions, sometimes we take care of the conditions. Okay, so we have got a very interesting formula that is called multiplication of theorem of probability, which is the formula which helps us to deal with the independent events. Now, keeping in mind the given formula, let us try to solve a problem. So I'm writing the question. The probability of the closing, the probability of the closing of each relay, probability of the closing of each relay of the circuit shown below is given by small p, full stop. If all the relays function independently, what is the probability that a circuit will exist between the terminals L and R? Let me draw the circuit for you. Very simple circuit I'm drawing. This is the terminal L, and this is relay number 1, this is relay number 2, this is relay number 3, and this is relay number 4, and this is your terminal R. So we can rename the relays as follows. We can name it as 1, 2, 3, and 4. What are relays? You are from electronics branch, so you probably know the meaning of the relay. Relay is nothing but electrically operated switch. And you know that when the relay remains closed, there will be a kind of circuit will form between the points L and R. Okay, and here when I'm talking about that the relays are actually functioning independently, that means sometimes it is getting closed and sometimes it is getting open. Nobody is manually operating the relay. Some sort of this particular circuit, which is actually in very simple situation, has been considered over here, because here we are not going to learn about the electronics intricacies. Here we are going to learn about how to apply probabilities. So somehow the system is in kind of this particular circuit is in a kind of physical system which is affected by the magnetic field, and the variation in the magnetic field actually makes the circuit automatically behave like that. Sometimes it closes and sometimes it opens, but it is the closing and the opening of the relays are independent of one another. So I want to find the probability that the circuit will be formed between these two relays. Okay, I have 4 minutes 58 seconds left, so I'm starting the problem. If I'm not able to complete the problem in this session, please join in the next session. Okay, today's class will be just one period class, but if I'm not able to complete the problem, you join the next session and then we'll continue. Okay, so this is the scenario. I hope that you have understood the scenario. And before I start solving the problem, we have to define the events carefully. So how many events are there? That is a very important task. So what we observe is that since there are 4 relays, there will be 4 events. And what will be the name of the events? That relay 1 is closed. This is event A1. This is relay 2 is closed. Okay, this is relay 3 is closed. Naming of the event is actually very essential before you start solving the problem by the axiomatic approach of probability. And relay 4 is closed. Okay, now probability of these events are given, and probability of each of these events is actually small p, for I is equal to 1, 2, 3, 4, as you can observe. Now, every event is associated with a complementary event. So if A1 represents the event that the relay is closed, A1 bar will represent the event that the relay will open. So consequently, we can write probability of AI bar to be 1 minus small p, where I is equal to 1, 2, 3, 4. Then we are going to solve this particular problem, and let's see what happens. Okay, I don't know what am I supposed to do now, because I know pretty much well that I'll not be able to complete this particular problem in the current session. So you have to join. I'm requesting all of you to join in the next session so that I can at least complete the problem. Because if a problem is started in a particular class, if I stretch it to the next class, everybody will lose interest. So you just copy the question in your, you just take a note of this question in your copy, and you just see that how the events are defined. And remember, the events, the relays are actually working independent of one another. So probably we are going to apply the multiplication rule of probability over here. And I think I have to wait for this particular session to end by itself, because if I forcefully end the session and rejoin, then again it will end, because because of this. I mean, actually, I'm using the basic version of Zoom. I do not have the pro version, and I'm not able to apply for the pro version because it requires credit card, and I'm not on credit. So let's wait. Okay, let's wait for the solution to be discussed in the next session. I hope that you are actually not feeling uncomfortable with the way I'm teaching. If you have any doubts in your mind or any question, you can ask me by unmuting yourself. Yeah, my voice is breaking because of this network connectivity problem, which I can't help. At least if you can see my whiteboard, then I think that will be okay. Because whatever I'm saying, I'm writing it on the board. So make sure that my whiteboard is visible to all of you. Just let me wait for the session to end. Okay, just hold on.